So, now we start the main course on PDE. So, next 4 hours, that means 8 lectures, 8 half an hour lectures, we will be discussing about the first order equations, and the main idea of first order equations is to introduce the concept of method of characteristics, and we give the idea about what is this method of characteristic, and the characteristic plays a crucial role in understanding the geometry and other issues related to PDE. So, we will have a detailed discussion about a method of characteristics restricted to first order equation. So, we will be doing first order equations, first order PDE. Okay. So, as we said, developing general theory as general as possible is the aim of this program. You will see that, but at the same time in the introductory talks I told developing a general theory even for linear equations is not feasible, but then there is a local general theory, local general theory for first order PDE. Okay. And that is the aim of this first course on first part of these first order things. Okay. So, let us recall the general equation, recall the first order PDE, recall this is what is. So, you will have an unknown x, that is the independent variable, then you have an unknown function, and then you have all your first order derivatives dx1 etc. dxn, sorry, dun by dxn equal to 0, where x is your x1 etc. xn, that is a general form of your first order equations. But as I said, this will be covered in 4 hours, but to make the ideas clear, we will spend the first 2 hours describing and analyzing this, introducing rather the method of characteristics in 2 space dimension, method of characteristics I told you in 2 space dimension. So, in 2 space dimension we use the notation xy instead of x1 y1. So, your equation is f of general equation f of x y u of x du by dx u of x y, it is a so you have your u of x y, that is your x y, and du by dx at x y, and then du by dy equal to 0. So, this is the equation initially we are going to discuss. After discussing the 2 variable case, we will go to the n variable case. So, we will start with an example to begin with, that is better. So, you have an example to motivate you what is this characteristics all about it. So, let us consider in this particular case where u is a instead of y I am trying to use for the time being u x t. The reason using is that t is something like a time variable. This is only for this example, later we will come back to the notation u x y. So, the PDE here, the u x t is your unknown with x is in R and t positive. So, we are doing it in the upper half plane. Okay. So, the PDE is ut plus cux equal to 0 for x in R, and let us look at this one where c is a constant. C is a constant. This is one of the simplest PDE, very easy PDE, first order, linear. This is a linear PDE. So, the life will be much more simpler. First order, linear with the constant coefficients. You see, it is also a constant coefficient PDE. Constant coefficient. So, I am going to solve this problem. You may have many questions after solving this problem. So, the problem is in the upper half plane. So, this is your x, this is your t, sorry, this is this is x, this is t variable. What I am going to do is I am introducing a curve. So, I take a point here x naught, or that point I will draw a line. Okay, that is a line, that line is okay. That line is nothing but x t is equal to c t plus x naught. This is the thing which I am going to do it. So, that I am introducing a curve here. So, introduce x t is equal to c t plus x naught. Here one point I want to think, this curve x t is viewed with respect to t. So, you have to view along this direction. So, that you have to view this as a function in t variable. Hence, the slope with respect to t is nothing but 1 over c. So, you have to understand. So, you are not viewing this x t as a line with respect to x. You are viewing this line x t with respect to the t variable. With respect to t direction, you are viewing it, and that is thing. So, that is a way you have to understand the slope of this one. So, that means you are looking for a curve dx x t for which dx t by dt equal to c. So, basically you are actually looking for a solution. You may ask a question why I did consider that equation, that you will come, that is precisely you are going to understand now here. So, once I do that one, I restrict my PDE to the line, restrict PDE to this line, to x t. That means, I will introduce a function as a function of t, my u t is equal to u of x t t. So, I restricted my t. So, this is a one variable function. So, I have a function u defined on the line c t. Once you fix x naught, it is a one variable one parameterized curve. So, I want to understand the derivative of u. So, I differentiate du by dt, that is nothing but differentiate with respect to x, but dx by dt equal to c, and differentiate with respect to u, and that is equal to 0. That means, what it gives you, that implies du by dt equal to 0, this one du by dt equal to 0, that implies ut is a constant along the line, ut is a constant along x t, that is what you got it, along x t. So, what does that imply? Ut is a constant along that imply. So, ut will be, that implies u at t will be u at 0, but u at 0 is nothing but u naught of x, right, because u naught of x. So, you prove that basically u of x t t will be, this is what you get it for each of these lines. Now, but I want to write, we need to write u x t generally. We need to write u of x t where x and t not just along the line. This representation of u of x t is along the line, but we want to write u of x t for arbitrary points. So, there is some minor issue, this is a very not minor, this is a very important issue. I will come back to that one. So, when you study. So, you have an x t here and then you draw this characteristic along that line with the slope. So, what would be your x naught here? This point will be x minus c t 0. But then you know that, so once you the so in the previous case what you are doing is that in the previous one, so you see you have straight lines along all the points. So, you have straight line, you are drawing lines along all these points, that is what you are doing it. But what we are doing in the next line, you are taking an x t and then drawing backward basically. So, it is a kind of inverse process, that inverse process is what makes our method of characterization little to not complicated, that is an important point to understand. We will tell about it more later. So, there is an inverse process going on. Given point on the initial thing, you can draw characteristics on one direction, but given a point there you want to make sure that there is a characteristic passing through that. These curves are called characteristic, we will come to that. There is a line passing through and then meets the x axis at that point. So, that way you can write that u x t is nothing but equal to u of x minus c t 0. But so, because along this curve x t that curve it is constant. So, u x t will be u of x minus c t 0. So, you get u x t finally is equal to u naught of x minus c t. So, that is a very nice example which you immediately see that, you see. So, you have, so if u naught is twice once differentiable, you can verify that u x t is indeed a solution. So, what is happening here? So, what this is called a wave travelling forward. So, the forward travelling wave, forward travelling wave. Okay. So, that is what happening. So, if you look at it at various plots, so if I plot it here, so this is I am plotting when t is equal to 0. So, suppose my initial profile is something like that, suppose my initial profile, this is my u naught given, then after some time it will move forward. So, with that time t equal to t naught, if I plot my u x t naught, I will get this okay, the curve will be like this. Okay. So, this will be moved forward little bit, okay. At that line it moves forward. So, this is what u naught u of x minus c t naught, that is nothing but u naught of x minus c t naught. So, this is nothing but the point x equal to c t naught. So, you see it moved. So, as t moves, so you have an initial profile, and as t moves the graph moves to the forward direction, and you can also draw a 3-dimensional picture of the same. So, that is what you want to have this example. So, basically you solve the problem du by dt. If you look at it, you got a problem u t plus c u x, and you have solved the problem u naught thing. So, you can ask many questions now. Why did I choose that curve x t? Is there a motivation behind choosing that kind of curve? So, you can ask many questions. So, you can ask question, why did I choose, why did we choose x t equal to c t plus x naught. Okay. Now, let us go back to one more thing. So, the one which we have considered is called an initial value problem. So, you have a problem u t plus c u x and your values of u naught is given here. That is what we have used it. The u 0, so I have not mentioned here. So, let me mention it here. This is my initial value. So, I am solving a problem u t plus c u x equal to 0 and then u at x 0 is equal to u naught of x. So, the initial value problem is given. So, this is an initial value problem. Okay. Initial value problem. Okay. So, what we have studied is an initial value problem. Okay. And so, the initial values, so let me write down this initial value u naught defined on the curve x equal to t equal to 0. So, the x axis. So, you have defined the initial values on the x axis. So, the why did I choose so the question is that, so you have a line here and you have all your initial curves here. This is your characteristic curves. This we call it a characteristic curves. Characteristic curves. Okay. And then in the previous problem I have defined initial values along this, but that is not necessary. If you look at it, I can define another initial curve. So, I can define an initial curve like that. Then again, so this also can be an initial curve. This also can be an initial curve. Initial curve. Because you know that u is constant along all these lines, and so if you know the value of initial value at this point, I can determine initial value along that curve. Similarly, if I know initial values and that point. So, you may ask a question, can I have my initial curves arbitrarily? That is not possible. Can initial curve be anything? Can initial curve, so you have initial curve be arbitrary? So, for example, I take this one and these are your curves, characteristics. Okay. So, and now suppose I choose an initial curve like this. If I choose an initial curve and my initial curve happen to be like this, you see, this is not possible. It will not solve the problem. It will not solve the problem. Why? Because you have initial curves here, and this initial curve, the values on that initial curve cannot be determined by this initial curve gamma naught. You see. So, that actually indicates that there has to be your initial curve should not be a kind of characteristic curve at any point of time. It should not be parallel. These are the conditions, geometry which you need to understand. So, if the initial curve is happen to be a kind of characteristic curve or a portion of a characteristic curve, then it is possible that many of the characteristics will not intersect your initial curve. So, to solve the problem, you have to see that very nicely every characteristic curves intersect your initial curve. So, initial curve eventually need to be a what is called a non characteristic condition. This condition we need to understand. So, you can have some sort of, it is not necessarily that initial values are prescribed in that x axis or something. So, we are trying to understand these things in a very mathematical way right now. Okay. But then the message is that, what is the message? The message is that we divided the domain, we divided not really divided thing, we divided the domain into characteristic curves. That is the one message, divided the domain into curves. And then that is a one message. Second message, we solved only ODEs, we solved only ODEs, we did not solve PDE. By solving your ODE we got your solution. So, look at here, if you look at it here, you see you have solved this equation, du by dt equal to 0, this is an equation you have solved. Of course, it is an easy equation, it will become more complicated, but you look at here, this is the second equation we have solved. So, you have basically solved two ODEs to solve your PDE. One ODE is solved to get the characteristic curves, another ODE is solved to get the solution, the property of the solution, which we got that the solution is constant along the characteristic curve. So, let us go to the next one. Okay. So, now we want to consider the general first order equation, we go is step by step. So, we will go first, we consider first order linear equation, first order linear. So, what is the first order linear equation? Your equation is axy ux plus bxy uy equal to cxy u plus dxy. Okay. So, this is your first order equation. Now, I want to give you the concept, what did we do, and then next, so you have a domain maybe in R2. So, you can have a domain in R2. So, you have a domain omega in R2, we will come back to that, and xy belongs to that. So, your PDE is defined in omega. Later we will come back to the initial value problem. So, first try to understand the how we introduce the characteristic curves. Okay. So, for that understand this equation. So, you look at fix xy point here, fix xy in omega. Okay. So, you are fixing a point xy in omega. Okay. And for that xy, what does this represent? What is aux plus buy? If you recall my preliminary lecture, you will see that this is nothing but the derivative of u, in the direction AB. That is what you in the previous lecture you have seen, direction AB, right. When xy is fixed, you will have a vector direction. So, this is given by A of xy, B of xy, you see. So, AB, which is a data given to you. So, AB produces a vector field in R2 for every, or a vector field in omega for every xy, axy, bxy produces a vector. That means on omega you have a vector field So, basically your differential operator part is nothing but the derivative of u along that direction. So, that motivates us to look for this motivates to look for a curve in omega, curve in omega. So, the curve will look like sum of with here t is a parameter, okay, x t y t, such that its tangent is a evaluated at that each point a of x t y t b of x t y t. So, let me go to the next page and explain x t y t. Okay. Okay. X t y t. So, you want to look for a curve. So, what happens that, so you want to look for a curve in your domain omega or R2 wherever the PDE is defined, on which at each point. So, this is the curve x t y t, x t, I am again telling you t is a parameter here, it is not the variable. On each point you have the curve. So, if this is x t y t for some t, at that point I need my tangential direction to be a of x t y t, okay, and that is what you are looking at it. So, every point has tangential direction a. So, everywhere there is a vector a x t, need not be parallel. So, what you are looking for is that you are trying to divide your domain omega with the curves has the property that its tangents are x t y t. So, you are looking for various curves for that x t y t. So, you are trying to fill up the region x t y t. So, what happens when you look at it? So, what is the equation of the curve? Equation, because its tangent is I of x t y t, thus dxt by dt should be a of x t y t. That is the equation, because you need tangent to be a b. So, the equation of the curve should be like this, dy by dt is equal to b of x t y t. Okay. So, if I define, so your curve is such that you are defined. So, once you know that you fix a point, if you fix a point in the same domain, I am giving different picture. So, fix a point x naught y naught and look for a curve here who satisfy. So, x at 0 is equal to x naught. So, you are looking for a curve x naught y naught is in omega, okay, this is in omega, it is a different picture, y at 0, and your ODE, the basic ODE will give conditions on A and B, so that it gives you solution. So, let me not get into that. So, you learn your ODE system, what are the conditions on A and B, so that there is a local solution. That means, when you have a local solution, every point on your domain omega there is a curve. So, you can fill your region, because every point if A and B are satisfied, you will have a thing. So, you will fill it up like that, and these are called the characteristic curves. Characteristic curves. Okay. And what happened to u? So, again define my along. So, once you have obtained a curve x t y t in omega, you restrict my u to the curve. So, ut is equal to u of x t y t. So, I am restricting my solution to that curve. So, you will get a one variable function with respect to the parameter t, and now compute du by dt. If I have my du by dt compute, I will have my ux and dx by dt, that is a, and u with respect to y uy with respect to b, and this is nothing but c u of x t y t will be u plus t. So, you see you have an ODE again here. So, what is done here? So, you have your domain omega, on that domain omega you have your curves, and these curves are obtained by solving a 2 by 2 system. On each of that curve you have your u, which is a u is given on each curve u is given by a u ut equal to u of x t y t satisfies ODE. That is what you got it, you see. So, if you know a function, so if you have your curve here and if you know the value of u at one point, because it is an ODE, it is a first order ODE. So, along each curve, so the curves are introduced in such a way that when your PDE is restricted to your that curve, it becomes an ODE. So, that can be solved if you know the value of u. So, you have to know what we call it an initial curve. So, if you have a curve which intersect your characteristic curves, which we call it an initial curve, okay, and on each of that initial curve, if the value of u is known to you, then you can determine u effectively. So, that leads to what we call the concept of a initial value problem, concept of or initial value problem, or this is also called Cauchy problem. Okay. Cauchy problem. So, let me describe the Cauchy problem, and then after that I will stop this lecture and then we will continue in the next lecture. So, on the Cauchy problem, so what is the Cauchy problem? You have your AUX, this is your BDE, BUY is equal to CU plus D, and then there is an initial curve, gamma naught is an initial curve. So, I will give a parametric representation of a curve. So, gamma naught is equal to some x naught of s, y naught of s, where 0 less than or equal to s less than or equal to 1. Okay. So, that is your initial curve, this is called the gamma naught. So, this we are going to use it. So, this understanding this characteristic curve is quite important. On gamma naught, so x naught s, y naught s is given to you, means the gamma naught initial curve is also given to you. So, you should understand what is given, initial curve is also given. Okay. And that initial curve, the value of u equal to u naught of s on gamma naught. Okay. So, this is your initial value problem, and find u, the problem is that find u in omega or in a neighborhood of that initial curve. So, this is the global solution existing, find u in entire domain omega or find u in a neighborhood of omega, neighborhood of gamma naught. That means, so you have a domain omega here, so you have your domain omega here, this is your omega. So, your characteristics here, and then you have an initial curve here, and the value of u is given along this initial curve. So, try to find u in the entire domain omega, or if not, at least in a neighborhood of omega. So, you want to determine u, this is what is called the locally determining, this is called the existence of local solution. So, you want to do that one. So, we will continue this process again, and I will tell you little more about it, and then we will go to what is called like Cauchy linear equation. And in the Cauchy linear equation, we will also state the theorem, what is the theorem, what is required by you. So, we will eventually write the theorem, general theorem, both linear equations and Cauchy linear equations together. But what you have to understand is the concept of characteristic and the meaning of initial value problem. Thank you.